Hello, my name is Tyler Schoen, and today I'm here to talk about my summer research project in researching the variational quantum eigensolver for simulating nuclear binding energies. So before we get into it, I'd really like to take a minute to just really thank my research advisor, Professor Maria Piroli, and the expert that we brought into our project, Dr. Alessandro Baroni. And they were very helpful to me along the way, so really thanks to them. It wouldn't be possible without them. And so what are we really doing here? So the problem is we want to find the ground state binding energy of a molecule. And the classical technique to do this is known as diagonalization. We don't have too much time to get into the math here, but basically this diagonalization technique is used to find the minimum eigenvalue of a Hamiltonian. And the Hamiltonian is a fancy word representing like the energy of the system. So in this case, that system would be the molecule. We use the deuteron H2 molecule as our base. But classically, this is a very time-sensitive technique. It is taking exponential time to solve, and this becomes exponentially difficult with larger molecules. So we would like to improve on that, and it has been proven that this algorithm we use is a big speed up compared to this diagonalization technique. So in comes quantum computing, and quantum computing is made up of quantum bits called qubits. These qubits are like your classical counterparts to qubits, which are regular classical bits, and those bits take on binary information of 1 and 0. Qubits are the same, except they have two special properties intrinsic to the quantum information involved. So the first property is that they have superposition. This means that the qubit can not only take on the state of 0 and 1, but also anywhere in between 0 and 1. So it could be both 0 and 1 at the same time, but once you measure the qubit, it is forced to collapse into one of those quantum states. So that means that we can determine certain probabilities that a qubit may collapse into 0 or 1, but until you measure the qubit, it exists as both. The other important property is entanglement. This means that if you measure qubit A, which is entangled to qubit B, qubit A turns out to be 1, you can infer that qubit B would also be 1, or would be 0, depending on the type of entanglement. So this is really powerful because this lets us really represent a lot of information with a small number of qubits, and the processing power is much more powerful than classical computers. So the background of this VQE algorithm is that it uses an optimization routine to approximate the ground state binding energy of a molecule. Keyword approximate. So it's not perfect, but we can get it down to within a certain percentage of error. So that's the goal. And it finds the minimum eigenvalue of exponentially sized matrices in polynomial time. So this is where the speedup comes in. And we won't get too much into the time complexity, but just know that it is a better solution than the classical counterpart. So the VQE algorithm, so first you have to determine the Hamiltonian, which is comprised of Pauli observables. Remember, the Hamiltonian, that represents the energy of the system. And these Pauli observables are like measurable quantities that, or measurable states that can be represented by these matrices, the XYZ and identity matrix. And once you determine that equation for the Hamiltonian, you would determine the expectation of observables in terms of state probabilities. So because we want to find the expected value of the Hamiltonian, which represents the expected energy, you thus have to find the expected value of each of those observables. So those can be represented by the different probabilities of measuring each of your different quantum states. So since we use 2 qubits, there are 4 possible quantum states: 0, 0, 0, 1, 1, 0, and 1, 1, meaning that the first qubit is a 0, the second qubit is a 0, the first qubit is a 0, the second qubit is 1, so on and so forth. And so, yeah, so those components of that equation are just representing the mathematical probability of measuring the system in that state. And once you can do that, you basically have a better equation for Hamiltonian, which can be used in the actual quantum computing after we measure those different probabilities for the quantum state, ending up in all of those different states. So once you have that equation ready, you can start the quantum system in an initial state, and then you modify that state by a custom gate, which modifies the state of the quantum system, and it's dependent on some parameter theta. So you then measure the probabilities of those qubit states, and you record what the probabilities ended up being. So in order to do that, you have to repetitively go through this process. We did it like 8,000 times per run. And then once we had all that data, you can configure the data into like statistical approximations of the probabilities. So then you know the different probabilities of the quantum system ending up in each state for that parameter theta. And using the Hamiltonian equation that we had before, you can find the expected energy of the system. So you just plug in the probabilities, you get the expected energy, and then you optimize on that. So then you change theta slightly, and then you redo the whole algorithm, and you keep doing that until you minimize the expected energy. Once you've minimized that, you return that, and that would be the ground state binding energy that we approximate. So one of the properties of quantum computers is that they're very noisy, in that when you go to measure a qubit, even if you expect it to be a 1, it might randomly flip and turn into a 0. So first, we need to code this algorithm out on a classical computer, which simulates how a quantum computer would act. So in other words, it's an ideal, perfect quantum computer that we have the luxury of using, because we're only using 2 qubits, and we're representing a simple molecule. So this is great for research purposes. However, if we were trying to simulate a very large molecule, we wouldn't be able to do this. So we simulate how a quantum computer would act, and we see this really nice curve with no noise, where the theoretical data almost perfectly overlaps with the experimental data. So you can't even see the blue line. However, once we add a noise model, which essentially says, okay, depolarizing noise, this says with some probability, right as we measure a bit, we might flip that bit. And when we add that noise to the model, you can see how the experimental data no longer overlaps perfectly with the theoretical data. And this noise is important because when we model that noise, we can then introduce algorithms to correct the noise. And once that algorithm learns how to correct noise, you can then apply it to a real quantum computer. And instead of adding noise to a real quantum computer, that computer has inherent noise. And your error mitigation algorithm can, after learning how to correct noise on this simple example, then it can go to a real quantum computer and actually correct the real noise. So the simplest example is with linear regression here. We basically map the noisy data to the exact values that we expect from calculating diagonalization on the Hamiltonian. We can figure out what should happen in an ideal quantum computer if we were able to run it infinitely and measure each time we get the perfect possible probabilities, and then the expected energy would be perfect. So we can map how the noisy data would map to those exact values. And once you do that, you know, okay, if I see noisy values at, if I get a noisy energy of 7 in this case for whatever these units are, you can go and map it to the exact value. So this is really strong. However, linear regression is too simple. It works really well here, but that's just because it's overfitting to this use case, and it wouldn't really work that well on a real quantum computer. But it gives you a flavor of how machine learning can be used to learn how noise interacts with the quantum system and fix that noise. So Qiskit, which is the proprietary language that IBM gives developers to interact with their quantum computers, it has a built-in noise model. And that noise model does not use machine learning, but rather it uses this matrix algebra formula, which you see at the top. And basically it finds a mapping matrix to convert the noisy state of the system to an ideal state of the system and vice versa. So that mapping matrix is learned by repetitively measuring the state of the system, and you can figure out the mapping and then just use matrix algebra to calculate what your mitigated data should look like. However, it turns out not to work super well when you want to add your own custom noise models. So here's an example of when we add the noise. It's, as we expect, there's not a perfect overlap between the experimental and theoretical data. However, when we add the built-in error mitigation, it actually makes it worse because it's just this technique isn't very suited for adapting to different kinds of noise models. So here just shows like linear regression actually works better in this case. Again, this is just not going to work on a real quantum computer as well, but it shows that machine learning would be a better approach to mitigating error. And so just to look at the results real quick, with the classical simulation with no noise, we still saw 6.6% error, which goes to show that, unless we repeat this experiment infinite number of times, there will still be some variation in the final results. However, what's really surprising is that we still got 24.5% error with noisy data on a classical simulation with the built-in error mitigation method. And on the quantum simulation with no noise added, but just natural noise from inherent quantum error, the built-in error mitigator still led to an 18.2% error rate. So it's clear that this method is not really that adaptable or great. So in the future, the most important thing would be to focus on how can we improve the error mitigation methods using machine learning. In this case, we used a neural net, or we used linear regression, but in the future, neural networks would be the probably the go-to thing to look into for improving error mitigation methods. And that's what we started doing towards the end of this project, but I didn't have time to get something really presentable. So yeah, in the future, that's the main thing that we should be working on. And thank you so much for listening to my presentation. If you have any questions, again, feel free to reach out. Here's my email, tshen@westhill.edu, and thanks again.